In the next few minutes, I would like to explain what thermal effects need to be taken into account when using piezoelectric sensors to measure single events. In the case of events with repeated thermal exposure, other effects may apply. Before jumping into the different thermal effects, we need to take a short look at the working principle of a piezoelectric sensor. In its essence, the load on the piezoelectric material generates a relative displacement of positively and negatively charged ions in the material. This results in an observable positive charge on one side of the piezoelectric material and a negative charge on the opposite side. This change is what we use to measure the force acting on the material. Our piezoelectric sensors incorporate one or multiple such piezoelectric elements. This is the heart of our sensors. When we take a look at this model of a piezoelectric sensor, we see that the pressure acting on the membrane leads to a force acting on the piezoelectric material. This is how we measure pressure, and the thermal effects we will take a look at all change how the pressure at the membrane affects the force on the sensing element. Now that we have the basics covered, let us review the three most important thermal effects for single event measurement. Let's take a look at our first thermal effect, the thermal drift. When temperature changes, the components inside the sensor change their length. This rate of change is dependent on the material properties and the design of the sensor. Minor differences in expansion of the measuring element and the surrounding components result in a change of force acting onto our piezoelectric material. This is observed as thermal drift, which is generally a slow process, and it can normally be eliminated from dynamic measurements quite well. The second effect to take into account is the thermal sensitivity shift. With the change of temperature, the stiffness of the components in the sensor change. This is again dependent on the material properties and the design of the sensor. Because of differences in these changes of stiffness, the distribution of the force acting on the sensor is changed. If more force flows from the membrane through the measuring element, then the sensitivity of the sensor will increase, and vice versa. This change in sensitivity cannot be eliminated altogether. Depending on the application and requirements for accuracy, a calibration with control temperature may be required to determine the exact sensitivity. The third and final thermal effect to consider for such measurements is thermal shock. Thermal shock is what happens when a very localized and fast change in temperature introduces a bending of the membrane of a sensor. This change in shape again changes the force acting on our piezoelectric measuring element. During highly dynamic, single event applications, the thermal shock normally affects the sensing element after peak pressure has occurred. In case the peak pressure is of interest and the thermal shock does not affect the peak, no additional measures need to be undertaken. In case the thermal shock overlaps with the actual measurement, the thermal shock can be delayed with the right accessories. Please reach out to your Kistler representative in this case, and they can help you with the right setup. Another critical effect is pyroelectricity. While Kistler sensors with piezostar or quartz as sensing elements are not affected by this, it definitely affects other piezoelectric materials, such as piezoceramics. In these materials, a change in temperature directly results in a charge on the surface of the piezoelectric materials, and with it, in an error in the measurement. This concludes the introduction of the most relevant thermal effects on piezoelectric measurements. For specific support for your measurement challenges, please reach out to your Kistler representative. And for more such videos, visit our Explained in X Minutes playlist.